Welcome back to CS with Lamyaa. This is episode 4, Linear Search and Binary Search. By the end of this lesson, you will know how both algorithms work, how to trace them step by step, and crucially when to use which one and why in your Pearson Edexcel 4CP0 exam. Let's get into it. In this lesson, here is exactly what we are going to cover. Number 1. Why computers need to search data and the two types of lists they deal with. Number 2. Linear search, how it works, a full worked example, the formal algorithm, best and worst case, and the Pearson pseudocode with a full explanation. Number 3. Binary search, a hook to understand the idea, the worked example first, then the formal algorithm, best and worst case, and the Pearson pseudocode fully explained. Number 4. A comparison of the two algorithms. This is a favorite Pearson exam question. Number 5. An exam-style practice question with a complete mark scheme. Think about searching for a book. Scenario 1. You walk into someone's bedroom. Their bookcase is a total mess. Books are in random order, there is no system at all. How do you find the book you want? You start at the first one, check it, not the right one, move to the next one, check it, keep going, one by one, until you either find it or reach the end. Scenario 2, you walk into a library. Books are in alphabetical order. Now how do you find your book? You open the catalog somewhere in the middle, check if your book comes before or after, and immediately throw away half the options. Then you do it again, and again, until you find it. Those two scenarios are the two searching algorithms you need to know. Key point: when you face a search problem, the data will either be ordered or unordered. If the data is unordered, you can only use linear search. If the data is ordered, you can use either, but binary search is much faster for large lists. Linear search, let's start with the definition, then we will see it in action immediately. Linear search is an algorithm that involves checking each item in a list one at a time to see if it is the right item. The word linear just means in a line you go through the list in a straight line from start to finish. Always starts from the first item in the list and check if it is equal to the right item. If not equal, then move forward to the next item to the right, and so on. The algorithm stops when the right item is found or when the end of the list is reached. The most important thing to remember: linear search works on any list, sorted or unsorted. You don't need to organize your data first. Now let's see it in action. We are going to trace a linear search before I give you the formal algorithm, because once you see how it works in practice, the algorithm will make perfect sense. Here is our list. Index 0, value 12. Index 1, value 45. Index 2, value 7. Index 3, value 23. Index 4, value 89. Index 5, value 3. Index 6, value 56. Now before I go on, I want to stop and explain something that many students find confusing. What is an index? Think of the list as a row of numbered boxes. The first box is box 0, not box 1, box 0. This is called zero-based indexing, and it is used in almost every programming language. So the number in box 0 is 12, the number in box 1 is 45, the number in box 2 is 7, and so on. When I say the value at index 3, I mean the value inside box number 3, which is 23. The index is just the position number. It is the address of each item in the list. Okay, now we search. Our target is 23. We want to find which index it is at. Step 1, index equals 0. The value at index 0 is 12. Is 12 equal to 23? No, move on. Step 2, index equals 1. The value at index 1 is 45. Is 45 equal to 23? No, move on. Step 3, index equals 2. The value at index 2 is 7. Is 7 equal to 23? No, move on. Step 4, index equals 3. The value at index 3 is 23. Is 23 equal to 23? Yes, found it. Return index 3. The algorithm stopped as soon as it found the target. It took 4 comparisons. We return index 3, meaning we tell the program the item you are looking for is at position 3 in the list. If 23 had not been in the list at all, we would have kept going all the way to index 6 before confirming it was not there. That is the worst case. You check every single item. Now that you have seen a concrete example, let me give you the formal algorithm. These are the exact steps that describe what we just did. Step 1. Take an ordered or unordered list of data and identify the item you are searching for, the search item or target. Step 2. Repeat the following steps starting from the first item in the list until you find the search item or until you reach the end. Sub-step A. Compare the item at the current position to the search item. Sub-step B. If the item at the current position is equal to the search item, stop searching. You found it. Sub-step C. Otherwise go to the next item in the list. Step 3. If you reach the end of the list without finding the item, report not found. Notice how those 3 steps map exactly to the 4 steps in the trace we just did. Step 2 is the loop that repeated 4 times. Sub-step A was our comparison each time. Sub-step B fired on step 4 when we found 23. Sub-step C is what moved us from index 0 to 1 to 2 to 3 each time. Now let's talk about performance, best case and worst case. The best case for linear search is when the item you are looking for is the very first one in the list. You check index 0, it matches, done. Only one comparison needed. The worst case is when the item is the very last one in the list or when the item is not in the list at all. In both situations, you must check every single item. If the list has 6 items, that is 6 comparisons. If the list has 1,000 items, that is 1,000 comparisons. Exam tip. Best case for linear search, sign item is first. Worst case equals sign item is last or not in the list. Now let's look at the Pearson pseudocode for linear search. I am going to go through every single line and explain exactly what it does, because this is what you will be asked about in Paper 1 and Paper 2. Here is the pseudocode. Set found to false. Set index to 0. While index less than length and found equals false do. If list open bracket index, close bracket equals target, then. Set found to true. Else. Set index to index plus 1. End if. End while. If found equals true, then. Send index to display. Else. Send open quote, not found close quote to display. End if. Now let me explain every line. Line 1, set found to false. This creates a variable called found and sets it to false. This is called a flag variable. It is like a switch. Right now the switch is off, meaning we have not found the target yet. The flag will be turned on, set to true as soon as we find it. Line 2, set index to 0. This creates a variable called index and sets it to 0. Remember, the first item in any list is at index 0, so we are saying start at the beginning of the list. Line 3, while index less than length and found equals false do. This is our loop. It says, keep looping as long as 2 conditions are both true. First, we have not gone past the end of the list. Index less than length means there are still items left to check. Second, we have not found the target yet. Found equals false means the switch is still off. As soon as either condition becomes false, the loop stops. Line 4, if list open bracket index close bracket equals target, then. Now here is the square bracket notation. List open bracket index close bracket written as list index means look inside the list at the position given by index. So if index is currently 0, list 0 gives us the value at position 0, which is 12. If index is 2, list 2 gives us the value at position 2, which is 7. This is how we access one specific item from the list. We then compare that item to the target. Line 5, set found to true. If the comparison matched the item at the current index equals the target, we flip the switch. Set found to true. This means the while loop condition on line 3 will now be false, so the loop will stop on its next check. Line 6 and 7, else. Set index to index plus 1. If the comparison did not match, we move to the next position. Index plus 1 means move one step to the right in the list. If index was 0, it becomes 1. If it was 1, it becomes 2, and so on. This is what moves us through the list one item at a time. Lines 8 and 9, end if, end while. These close the if block and the while loop. Lines 10 to 14, after the loop ends, we check whether we found it. If found equals true, then we output the index where it was found. Else we output not found. That is the complete linear search algorithm in Pearson pseudocode. Every line has a clear purpose. The found flag controls the loop. The index variable tracks our position. The list index notation accesses one item at a time, and after the loop, we check the result. Now we move into binary search, and I want to start with an example straight away, before I explain the formal algorithm. Think of the game. I am thinking of a number between 1 and 15. You can only ask questions and I will tell you, higher, lower, or correct. What is your first guess? If you are smart, you guess 8, the middle. I tell you, lower. Now you know the number is somewhere between 1 and 7. You have just eliminated 8 items in one guess. Next you guess 4, the middle of 1 to 7. I say, higher. Now you know the number is between 5 and 7. You guess 6, the middle of 5 to 7. I say, higher. The only remaining option is 7. You have found it in 4 guesses out of 15 possible values. That is exactly how binary search works, and this brings us to the most important rule. Critical requirement: the list must be sorted in ascending order before binary search can work. If the list is not sorted, binary search will give you wrong answers. You cannot use binary search on unsorted data. Exam tip: if an exam question gives you an unsorted list and asks you to use binary search, stop. You must use linear search instead. This distinction earns and loses marks every year. Now, let's look at the formal algorithm for binary search. Step 1. Take an ordered list of data and an item to search for. Step 2. Maintain a range where the target might be found. Initially, the range is the entire list. Think of lower and upper as 2 arrows, lower points at the first item in your current search zone and upper points at the last item. At the start, lower is at index 0 and upper is at the last index. Together, they define the boundary of where we are still searching. Step 3. Repeat the following steps until you find the item or the range becomes empty. Sub-step A. Find the item in the middle of the current range, the midpoint. The formula is middle equals lower plus upper div 2. Let me explain why this formula works. Lower is the index of the left boundary. Upper is the index of the right boundary. If you add them together and divide by 2, you get the index exactly in the middle between them. For example, if lower is 0 and upper is 6, then 0 plus 6 equals 6, divided by 2 equals 3. So the midpoint is at index 3, the exact center of the list. Div means integer division. You always round down if the result is not a whole number. Sub-step B. Compare the midpoint item to the target. Look at the value sitting at that middle index and ask, is this the item we are looking for? Sub-step C. If the midpoint item equals the target, stop. You found it. Return the middle index. Sub-step D. If the midpoint item is less than the target, set lower to mid plus 1. Let me explain exactly what this means. If the midpoint value is less than the target, it means the target must be somewhere to the right of the midpoint because the list is sorted in ascending order, all bigger values are on the right side. So we no longer need to search the left half at all. We throw it away completely. We do that by moving our left boundary lower to one position after the midpoint. Lower becomes mid plus 1. Now our search zone has shrunk to only the right half. The upper boundary stays exactly where it was. Think of it like this. If you open a dictionary in the middle and the page says M, but you are looking for a word starting with S, you immediately know S must be to the right. So you grab only the right half and throw the left half away. That is exactly what lower equals mid plus 1 does. Sub-step E. If the midpoint item is greater than the target, set upper to mid minus 1. This is the mirror image of step D. If the midpoint value is greater than the target must be somewhere to the left because all smaller values are on the left side of a sorted list. So we throw away the entire right half. We do that by moving our right boundary upper to one position before the midpoint. Upper becomes mid minus 1. Now our search zone has shrunk to only the left half. The lower boundary stays where it was. Back to the dictionary, you open it in the middle and the page says S, but you are looking for C. You know C is to the left. You grab only the left half. That is upper equals mid minus 1. So to summarize the logic of D and E in plain English, lower equals mid plus 1 means start searching from just after the midpoint, go right. Upper equals mid minus 1 means stop searching just before the midpoint, go left. Together, these two lines are what give binary search its power. Every single comparison cuts the remaining search zone in half. Step 4. If lower ever becomes greater than upper, the range is empty. There is nothing left to search. The item is not in the list. And that's a wrap on part 1. We've covered everything you need to know about linear search: the definition, the step-by-step trace, the algorithm, best and worst case, and the full Pearson pseudocode. If that clicked for you, drop a like. It genuinely helps this content reach more students. In part 2, linked right in the description, we move on to binary search. We'll walk through the algorithm, a full trace, performance, pseudocode, and then compare the two with an exam-style question. Don't skip it. Binary search is where students lose easy marks. See you there.